So now we're into rigid body dynamics, or I don't know, rotation. I always call it angular mechanics. Keep in mind these are the same Suvat equations. You had minus. Oh no, here they all are. There they are. I was going to say minus this one, but I'm just not seeing it right. That's final angular velocity. That's initial, right? So just remember the angular equivalent is theta. This one is omega initial. This one's omega final. This one is alpha. This one, the angular equivalent of time is time. Okay. Honestly, I just use Suvat when I'm writing stuff down, but you do want to convert. I don't think they're going to give you revolutions per minute. I did just because you're going to be engineers and probably in the United States. And we don't believe in the metric system. But yeah, you definitely want to do stuff in radians per second, per second. Okay. And then we're going to make this great analogy, right? So in place of mass, we've got moment of inertia, right? And so that's this guy, right? It's going to be some constant times mr squared, right? So like a cylinder is 1/2 mr squared. A mass on the end of a stick is mr squared. There's all these ones, right? A sphere, I think, is 2/5 or something like that. But they're going to have to give it to you, right? Okay. And then this is just F equals ma, right? Right. So torque, which is the angular equivalent of force, right, is equal to the angular equivalent of mass times the angular equivalent of acceleration, right? Okay. This is the equivalent of momentum is mv, and this is conserved in the same way that linear momentum is, which is super cool, right? And then this is change in momentum is force times time, right? We've seen that on the Suvat side, right? Okay, and then change in momentum. We didn't have this one, I don't think, in the momentum equation, right? Change in momentum is the change in I omega. Oh, that's fun. Yeah. Okay. You could say I delta omega or delta I, because we can change the moment of inertia, which is kind of fun, right? Hard to change the mass of an object, right? Okay, but you can change the moment of inertia. Like, for example, a ice skater can pull their arms in and change their angular, their rotational inertia, their moment of inertia, right? Okay. But anyway, there's that, right? And then this is our energy equation, right? Oh, end the show. I don't want to do that. If we end the show, what happens, right? Okay. But anyway, this is the same as kinetic energy is 1/2 mv squared equals p squared over 2m, right? So they're just showing you those same equations there. And of course, angular energy is conserved, angular momentum is conserved. I think I like angular mechanics more than my students do. But remember also in the angular section that you've got to do the relations, the tangential relations. And you only have this one in the data packet. V is omega r. And that's in like the previous section or something, right? But we also have displacement on the edge, right, along an arc. So if you have a wheel like this, right, and you go, it's got some radius like this, right? Okay, the displacement along this edge here is theta times r, right? And then acceleration, the linear acceleration of some object, if this wheel is speeding up, okay, the linear acceleration is alpha r. These guys are worth memorizing. It makes sense, right? You can remember this. This one's in the packet. You can remember this because of maths, right? Your math teachers taught you that, right? Theta is just the arc length over the radius, right? But yeah, these should be in there in my opinion, but they're not. So they just think they're so obvious but you'll use this, right? So if a wheel, if a skateboard or a car moves some distance, and you know the radius of the tires, you can get the angle from that, for example. Okay. Make sure it's radius. Double check radius. I think half the time when I get problems wrong for angular mechanics is because I use the freaking diameter instead of the radius. And hopefully I disabused you of that, but I'm just a spaz. Anyway.